Hello friends, welcome to this new video lecture on amortized analysis. Now in this lecture we are going to do amortized analysis using accounting method. So let's get started. So first let's understand what is amortized analysis. Now in an amortized analysis we see that a part of the algorithm is slow and not the entire algorithm is slow. So in that case we know that the part of the algorithm which is slow is going to cost us. Okay, it's going to be something very expensive. It's going to take more amount of time to execute. So let's understand, like, just let's say that it's an operation wherein suppose we are doing matrix multiplication. So we might have three nested for loops, one inside another. So the complexity might go up to n cube or n raised to 4 in some cases. So there can be many such cases wherein only a part of the algorithm is slow. Now you can see that suppose this is the length of my algorithm. Now in this algorithm only a part is slow. So can we in any way distribute the complexity throughout all the operations inside the algorithm? That is amortized analysis. Because if we distribute it, then the overall algorithm will bear the cost of those expensive operations. And that's how we'll be having a reduced cost per operation. So let's see how we are going to handle amortized analysis using the accounting method. Now, there are actually three methods using which we can solve this: the aggregate analysis, the accounting method, and the potential method. And there are three examples using which we can make a person understand how these particular techniques work. So there are the examples like dynamic tables, stack operation, and binary counter. So in this video lecture, we are going to only focus on accounting method. So let's start. Now, what is an accounting method? We assign an amortized cost to each operation, where the actual cost might be lower or higher than the amortized cost. So the sum of all the amortized costs in a sequence must be at least the sum of all the actual costs. Since we would like to bound the total cost of the sequence by the sum of amortized cost. Now, how do we ensure this property? What does it really say? It just says that there might be some actual cost associated to an operation, but let's have some other kind of cost charged. So this other cost that is charged, we can call it an amortized cost. This amortized cost could be greater than the normal cost, or it even could be lesser than the normal cost. But one thing we need to ensure when we are working this entire thing, that the amortized cost is never less than the actual cost. That means whatever we are going to charge a person should always be more than the actual cost. We'll see to it that it never goes below zero. It never goes negative. So what is an accounting method? Now you see the formula over here. Okay, so the CI is the actual cost throughout n operations, and when we do the summation of all the costs throughout n operations, it is less than or equal to the amortized cost throughout all the operations, right? So this is how we work. So let's understand this entire video with the help of a banking example, wherein just let's say that whatever is the extra cost charged to the person will be stored in the bank. And supposedly sometimes when the actual cost is more than the operation cost that has been charged, that is the amortized cost, then we can take something from the bank to take care of the extra cost that has been charged. So that's how we'll be working. So let's understand this entire scenario with the help of examples. Okay, so now we have dynamic tables. So now in case of dynamic tables, you see that a fictitious amortized cost, that is CI dash, is charged. It is said that one unit of work is done in $1. But are we going to charge $1 or more? So let's find out. So the fee is consumed for the operation. What fee? The $1 fee. Any amount not immediately consumed is stored in the bank for use by subsequent operations. Now, the bank balance must not go negative. We must ensure that. So the bank balance is dependent on which cost? The amortized cost, right? So we'll have to see to it that the actual cost is always less than or equal to the amortized cost, right? So that means the total amortized cost provide an upper bound on the total true cost. Now, so this is the dynamic table wherein we'll see that if we want to do an insert operation on a dynamic table. So we all know what is a dynamic table, right? So dynamic table is like a hash table wherein we'll insert the elements into the different hash position as per the hash values, and as soon as the locations gets filled up, we double the size of the table and we copy the existing elements inside the new table, and then we free the old table. So that's how we work. But we all know that an insert operation just costs us $1, but there is some other cost that is more expensive cost. What is that expensive cost? The expensive cost is of doubling the old array, okay, the and actually allocating a double the array size of the old array and copying the existing elements. So you can see the above for 8 elements, whatever it might be, they might get copied into the new array. So that is the extra cost. Okay, so you can see that like though while I'm inserting an element, the insertion just should just take $1. Okay, but still I could ask a person for extra few dollars, right? So what is accounting method? Okay, we can say that in accounting method we are prepared for some kind of situations. It's like investing into your future, so that if later in life you face any kind of troubles, you need an extra extra money or something, then you can just take it out from the balance that you have stored, that you have accumulated throughout years. So that is accounting method, that is getting prepared beforehand for the worst to come, or for better investments, whatever it may be. So it means we are going to charge extra for each operation that goes on. Now, so we can see that uh, supposedly this four dollar zeros that you can see has come out from the previous array, which was of size 2. So the size 2 thing, okay, when it came down, it became 4 elements. Now after these 4 elements, new 4 elements were added, and every one were charged $3, wherein for insertion $1 was taken and rest $2 was stored for further use. So you can see we have accumulated $8 extra. So now as you see that this particular table is filled, and if you want to insert a new element, we have to double the size. So you know that the cost of doubling and then copying it is $2, right? So you can see I have created a new array, and obviously when I copy the entire old one into new one, you'll see that slowly that $2 gets utilized, and finally I don't have any extra amount left for those transactions. Now, so now we have understood the working. Let's see how it works, okay, throughout. So we'll take the example of a bank, and we'll see how at each step we take the amortized cost and how the bank value changes accordingly. So now in this example, you see that I have the first element, that is 1, and the size of the array that I'm having is also 1. So to insert it, we need a cost of 1. But still I charge an amortized cost of 2. That means I'll have 1 extra as a balance because the actual cost needed is 1. So I store that extra balance in the bank, and you can see for the ith operation in the bank I have 1 extra credit. Now you see in the second operation I need to double the size of the array because the size is 1, so I need to double it to 2, plus copy the old element and insert the new element, right? So you know the cost of copying and doubling one element of the previous array to the new is 1, plus the insertion of the new element. So that means we are dealing with 2 elements, that is the new element and the old element that has to be copied from the old table to the new table. So in that case, we'll need the actual cost of 2, but what is the amortized cost charge? That is 3. So you can see again 1 extra is charged for it, and that goes into the bank. So you know already we have a balance of 1, and 1 more gets added, so we have a balance of 2 now. Now you can see for the third element, in the on the third element, we see that the array is again full. The size is just 2, so I need to double it. I double it. So doubling means what? Copying the previous 2 elements into the new array. So that would cost us 2, and the insertion of the third element that would cost us 1. So the total cost needed is 3, and the amortized cost, that is charge, is also 3. So there's nothing left to be put in the bank. Okay, everything has been used up. So you can see the bank balance remains the same. Then let's proceed and understand the insertion of the fourth element. When we insert the fourth element, the size is 4, so we need not increase the size. So the cost of insertion is just 1. Still, I charge 3 credits. So in that case, 2 credit is extra. So I have the previous balance as 2. I add the new 2 and I have the total balance credit as 4. Now, for when I go for the fifth element, I have to copy the previous 4 elements into the new table because my size needs to double. So copying of the last 4 elements will charge me 4, plus the insertion of the new element will charge me 1. So that will be total cost of 5. But can you see now in this case the cost needed is higher than the amortized cost. Still I just charge him the same amortized cost. So where do I get the extra credit needed to compensate for the extra 2 credits needed in the actual operational cost? We can take it from the bank. In the bank we have 4 credits, so I take 2 out of it. So I use this amortized cost of 3 plus 2 from the bank to maintain this operation. Okay, so as I've taken 2 from the bank, what left in the bank is 2, right? So now for the sixth operation, you can see that the array can hold it clearly as the size is 8. So the actual cost needed is 1. I take 3, so that is 2 credits extra. So in the bank I have 2, I add the new 2, so it becomes 4. Similarly, in the case of seventh element and eighth element, you can see that in the seventh element again, I just need 1, but I take extra 2, which goes in the bank and makes it 6, balance as 6. For the eighth element, I just need 1, but I take 3, so extra 2 gets added again to the bank and it becomes 8. But you can see for the ninth element now, when I have to do the ninth element, as the size of the array is just 8, I have to double it. When I have to double it, I have to copy the previous 8 elements plus insert the ninth element. So that means the total cost needed would be 9, but I'll just charge 3 from the person. So can you see this? These are the worst times wherein obviously you are being charged extra, but obviously you have something in the bank which you could use. So you need not panic in such cases. Okay, you are just charged the same amount and rest is taken from your bank balance. So you can see the 3 that is charged normally, we need extra 6 which is taken from the bank. As we take 6 from the bank, only 2 remains in the bank, and that is how it goes. So you can see for the 10th operation, again there's no cost for doubling or anything, just cost of insertion. Still I ask for extra 3, and you see that I have 2 left, so this should become 4, right? So that is how we work. Okay, now in this case we can also say that at the start we could have just taken one like as the amortized cost, because even if we had started with $1 or 1 credit and not 2 as the amortized credit, still we wouldn't have gone less than 0. So even in that case we could have started with just 1. Okay, so now that is it. Now you can clearly see that in the last example in the dynamic tables we handled the expensive cost very easily because we were preparing from the start. That means we were charging extra from the start. So that was working with dynamic tables. So now in this case, we are going to go ahead and we are going to understand the accounting method with the help of a stack example. Okay. So now let's start with the stack example. So you know that in stack we have two main operations, that is a push operation and the pop operation. In the operation, we push elements into the stack, and in the pop operation, we take out the element from the top of the stack. So we know that the actual cost needed to run these two operations is a constant time operation, because the push function, what it does, it just checks whether the list is like not full. So it checks whether the top is not equal to the array size. If it is not, it so that costs us just big of 1, the if statement. Then it actually inserts the element, that's an assignment to a particular position in the array. Even that is a constant time operation, big of 1. And finally we increment the top, so even that is a constant time operation. So we can say that the push operation completely is a constant time operation. Similarly pop, we check whether the top is actually not equal to -1. That means the stack is not empty. If it is not empty, we take out the first element, we decrement the top. So whatever we do, it's all constant time operations. Okay, so we know that if it is a constant time operation, then the cost will be just big of 1. And if we do this constant time operation for n operations, then we can say that it would result into big of n time complexity. So let's understand that how we are going to use amortized cost in this case. So we again see that the amortized cost is going to be higher or lower than the actual cost, and we'll always see to it that the total amortized cost is greater than, right, or equal to the actual cost, or and not less than it. So we can say that in this case we can see 3 operations: push, pop, and multi-pop. And we know that multi-pop can be an expensive operation. So in this multi-pop function, we can see that we have the complexity of minimum of k comma s. What is k? The number of elements that I want to pop out. right? And what is S? The number of elements inside the stack. So obviously the complexity will be dependent on the stack of the size of the stack as well as on the number of elements I want to pop out. If suppose my stack has 100 elements but I just want to pop out 60 element, which is k is equal to 60. So the first 60 elements, if I pop out, the complexity would be just 60, right? But if I have suppose only 40 elements inside my array and I want to take out 60, so obviously the number of maximum number I can pop off is just 40. So that's why we work with the minimum elements that is there between k and s. But what is a multipop operation? If we say clearly, multipop operation is what? It is basically pop operation, but multiple times. But we say we know that multi-pop operation, even if we call it once, we can take out all the elements inside the stack. That means the worst case complexity for multi-pop can go up to big of n, right? And if we do multi-pop operations for n times, then it would lead to n into big of n, that becomes big of n square. But obviously we want to reduce it, so let's see how we do it. Okay, so for each operation in the sequence, we can say if the amortized cost is greater than the actual cost, then the difference is stored as credit with an object in the data structure. If the amortized cost is less than the actual cost, then the stored credits can be used to make up for the difference. So it's again like the bank wherein I store the extra cost and later I use it whenever it's needed. So we have to use the stored credit when amortized cost is less than the actual cost to make up for the difference. So that sum of cost is always non-negative. Okay, so we can say that let's assume that instead of just charging one for push, one credit for pop, okay, we can directly start charging for the push itself. We can charge 2 credits. That means we can have one extra credit stored every single time the push is done. So obviously we know that number of pop functions can't exceed number of push, right? And even if we call multi-pop, it is what? It has a subroutine as pop function, right? So obviously it can't go more than n elements that has been pushed inside the stack. So it clearly states that the final complexity is going to be big of 1, right? And both for pop and multi-pop, we need not charge anything because it was taken care of in the push operation itself, right? So here we have an example of like having a stack of plates. So whenever I keep a plate, I actually like pay $2 so that when I again have to pop a plate, I don't have to fill up anything, right? So as we are putting up a stack of plates and we know that we have filled when we were putting up. So when I'm taking the plate again back, okay, I can take one plate or multiple plates as multi-pop operation, but we need not pay for it anytime, right? So that is the example. So this is the accounting method. Now let's proceed with binary counter and understand how accounting method works in binary counter. So we know this table. In this table we see that as we call this function, in this function we pass the first array, that is all zeros. Okay, and we see that as we encounter the first zero, okay, we can't go inside the while loop because the while loop demands for the element to be 1 and the I to be less than k. So I is obviously 0, that means we are starting for the first element, right? But as we don't have a of I equal to 1, we don't go inside the while loop and we just check whether I is less than, can we increment the value of a of I, we assign it as value 1. So you can see this particular row has an output as the second row because the first element it was encountered was changed to 1, right? Then we send the second array completely to this increment function and you see as we see the first element 1, okay, we go inside the while loop, we change it to 0, okay, and then we increment to the next value of the array, index of the array, and as this is 0 we come out outside the while loop because in while loop we need it to be 1. As we come out we just change the value of it to 1. So you can see this 0 has been changed to 1, right? So the third row is the output of the second row. Now we give third row as the input and you know that as soon as 0 is encountered we change it to 1. So you can see not much changes, only the first bit has been changed. Similarly, you can, now the best difference you'll see between the when fourth row is given as the input and fifth come out as the output. So you can see we have 1, so that means we go inside the while, we change that into 0 and then we increment the index. Okay, so you can see 1 has been changed to 0, second 1 is also getting changed into 0, and finally when we increment I encounter a 0. So I come out outside this while loop, I check whether the index is less than k, yes it is less, so obviously I'll change a of I equal to 1, so you can see the 0 getting converted into 1. So that is the output as the fifth row. Now we have the number of bits in the array as k, which is equal to 4, and we can see we can get 2 raised to k sequences, right? That means we have 16 rows, 16 combinations we can get, right? So we can clearly say k equal to log of n. So that is a binary counter. But let's see how it's been charged and how accounting method takes like the care of the binary counter method. So you can see that in this case, whenever I'm doing the flips, so the like every single time when there's a change in the sequence, there is one bit change of a flip from 0 to 1. So you can see 0 to 1 is happening almost one time at least, and not more than one time actually. It is just happening for one time in every sequence. Okay, so you can see in the first one 0 to 1. In the second one, this 0 to 1 has been changed. In the third one, this 0 to 1 is changed. So we can say that we are charging $1 for every flip from 0 to 1. And similarly, I can see there's flip from 1 to 0. So flip for 1 to 0 is again charged $1, but in some cases you see there are more than 1 to 0 flips in the same operation, right? So you can see that these are like expensive, right? Because we don't know when it's going to happen, and it suddenly comes up asking for a higher cost because there are more than 1 to 0 operations. So you can see $3 is also charged. So obviously the base cost has been taken in the flip 0 to 1. So can we handle the expensive cost in the base cost itself? Yes, we can do that if we charge a bit extra for every flip from 0 to 1. So let's see how it happens. But we know that the worst case could go up to what, nk. How nk? Because suppose we're having n operations and suppose all the k bits gets changed, right? So if all the k bits gets changed in one operation, k bits, right? So if for every operation, if it leads to k bits of changing, so it will lead to n into k, right? Big of n into k. But that's not the case now. So what we can say is that instead of charging just $1 from 0 to 1, the flip from 0 to 1, we'll charge $2, so that 1 remains extra with us. Okay, and for every flip from 1 to 0, we won't charge anything. That is $0, right? So we can do that. Okay, and when we flip it, okay, it's nothing but the increment operation is just what it takes a runtime complexity of big of 1. Now, so in this table, it's pretty clear how we are going to work this out. So you can clearly see that instead of charging just $1, we are charging dollar through 2 for every flip from 0 to 1. Okay, so you can see in the first operation itself, okay, when this 0 to 1 was converted, I took $2. So in the bank, I had $1 left. Okay, because one was for changing the bit and one is extra, which I keep in the bank. Okay, in the second flip, I see that one bit is going from 0 to 1 and this one bit is from 1 to 0, right? So in the old one, I would have charged $1 for 1 to 0 flip. But you know what? I'm not charging anything now because I have extra in my bank. Okay, but am I using the bank also? No, I'm not, because I'm charging $2. So all these two, both these two operations are taken care of in $2 that I'm charging, and still the bank balance remains to $1. Then again you see that I don't have any 1 to 0 operation, 1 to 0 flip in the third operation, but I have obviously 0 to 1. Okay, so with 0 to 1, this is getting converted to 0 to 1. You can see that very clearly. And for that, obviously, I'm going to charge $1, but obviously, amortized cost is $2. So you can see one extra dollar has been charged, which goes into the bank. So $1 plus $1 becomes $2. Right now, in the next step, you see that I am taking in changing two flips from 1 to 0. Okay, though they should have been charged $2 because there are two flips, but we don't charge anything to them. Okay, and there's one flip from 0 to 1. So now let's see how that has been taken care of. So in this particular row, I'm again charging $2, wherein there are three flips actually going on. So we need $3. So that means I'm going to take one from the bank. In the bank, I have $2 extra. So I consume one from the bank. So that leaves the bank balance to $1. Similarly, I go ahead in the next operation. You clearly see there's only one 0 to 1 flip. I charge $2. So $1 extra, which goes into the bank, makes it $2. Right. Now again in the next flip you see there's 1 to 0, there are two flips actually happening, 0 to 1 and 1 to 0. So for 1 to 0 obviously $1 should have been charged, but I'm not charging anything. I'm entirely taking $2, which is therefore two operations, and the bank balance remains the same. Similarly in the next operation you can see only 0 to 1 is done, right? But I still charge $2, so $1 is extra, so the bank balance turns to $3. Now in the next operation you see there are three flips happening from 1 to 0, and there is one flip from 0 to 1. So you can see $3 should have been charged for all these three flips from one to zeros. Okay, but I don't charge anything, right? And I just keep on charging $2. But how much do we need in this operation? We actually need $4. So $2 is then charged in this current operation as used up, and I can take two extra dollars from the bank. So you can see the bank balance goes from $3 to $1. So similarly, we proceed ahead, and that's how I don't have to charge ever extra, or I need to have an expensive operation. It's been taken care of by whatever collection I'm doing from priorly. Okay, so that's how I use up that particular money, and that is how it goes. So this is a reference link where I took like some understanding. Thank you so much. I hope you have enjoyed the lecture of how accounting method works, how we save from the beginning to take care of whatever happens. So in this pandemic, you might have realized how we have taken care of things with the help of our savings. So this is it. Thank you so much. Happy learning. Enjoy algorithms. Thank you.